Hello, everyone. Welcome back after the summer break for this new appointment of our 40 under 40 lecture series, the first one of the new academic year. And yeah, I wish you all the best wishes for this for the new academic year. It's a pleasure today to have with us for this first lecture of the new year. Academic year, Professor Alison Ferris, Alison M. Ferris. She is an assistant professor in the Department of Mechanical and Aerospace Engineering at Princeton University. Alison's research interests include using shock waves and optical diagnostics to study the design, chemical synthesis, and reaction kinetics of sustainable fuels for use in current and next-generation energy and propulsion systems. Alison received her PhD in mechanical engineering from Stanford University in 2021, focusing on the development of a high-temperature laminar flame speed measurement technique and a combined gas chromatography laser absorption diagnostic for time-resolved species measurements behind reflected shock waves. She received her MSc in mechanical engineering from the University of Wisconsin-Madison in 2014. Alison, it's really a pleasure to have you here, and we are looking forward to your lecture, so please, the floor is yours.
Great, thank you very much, Salvatore. And I also just wanted to say thank you generally to the Belgian section of the Combustion Institute for organizing this lecture series. I think it's a great opportunity for us to hear about what the up-and-coming and young researchers are up to these days, as well as it helps also give us some visibility on our own research. And so I just wanted to say thank you for the invitation. I'm happy to be here and excited to talk about ammonia kinetics. So the title of my talk is Ammonia Kinetics. Are we there yet? And so what I mean by that is, are our kinetic models for ammonia pyrolysis and oxidation, are they satisfactory, or do we still have more work to be done? And more specifically, is there more experimental work that we should be doing to help us get there? And so there have been a number of talks, even in this e-lecture series, on ammonia kinetics. And so I wanted to just emphasize that I'm an experimentalist. So what I'm presenting today is an experimentalist perspective on this problem. Before I dive in, I wanted to mention I am currently an assistant professor at Princeton. But the experimental work that I'll be presenting today comes from my time as a research scientist in the Hansen Research Group at Stanford University. All right, so today in my talk, I'll first start by giving a high-level overview of our general interest in ammonia, as well as a high-level overview of the experimental data that we currently have available for optimizing and validating or verifying the performance of ammonia kinetic models. After that high-level overview, I'll then dive into one particular shock tube study that we conducted recently. And this is looking at ammonia oxidation, specifically multi-species measurements that we conducted in a shock tube. I'll talk about the optical diagnostics that we used. I'll talk about the results, and then I'll dive into some kinetic analysis. All right, so an obligatory slide on why are we interested in ammonia. So ammonia in particular has garnered a lot of attention recently as a carbon-free fuel alternative. And that's due to its a number of advantages. So first and foremost, it contains no carbon, right? It's nitrogen, free hydrogen atoms. It's also readily liquefied for transport and storage. And in fact, there's already a lot of these facilities already in place due to our use of ammonia in fertilizer production. However, ammonia does have a number of disadvantages, as we're well aware in the combustion community. So specifically, when we start looking to use ammonia as a fuel or to burn it, we know that it has a low flame speed, it has narrow flammability limits, and it also has a long ignition delay time. So all these mean that we cannot just drop ammonia into our existing propulsion devices. We do have to figure out ways to improve it and make it more usable for user-friendly, put it that way. Another disadvantage, though, is that due to the fact that there's nitrogen in the fuel itself, we often see higher NOx emissions, and it's also toxic. Although, to be fair, a number of our other fuels are toxic as well. And so recent research efforts in our combustion community specifically have focused on enhancing and improving our understanding of ammonia combustion behavior, whether that's looking at ammonia on its own, or looking at ammonia as it is reacted with other fuel types that might help enhance its ignition behavior. And so these research efforts have really taken off. And so I wanted to look into sort of some metrics for understanding, right, in what way are we in the era of ammonia right now? And so first and foremost, if you just look on Google and use their Ngram viewer, for example, this is a tool that allows you to search in books and look for the how frequently a set of terms are used. And so what we see is if we search for ammonia combustion, basically ammonia combustion has shown up in books very frequently, specifically just in the past few years here. And just for context, if we look at how frequently we mention or ammonia fertilizer is mentioned in books, we say that that's tapering off, and then we've actually even surpassed mentions of ammonia fertilizer or fertilizer use, and we're well on our way to reaching the peak of essentially ammonia fertilizer mentions in books and in historical context. I also wanted to look into specifically within our combustion community, how significant a role does ammonia research play in what we do? And so I've been in this community for about 5 years now, or not 5 years, more than that, but 5 combustion symposia, we'll say, so about 10 years now. And so as we know, this is our event that's a major conference that's held every 2 years. And so I went back and looked through the programs just to see, how many papers were we publishing on ammonia over the years. And so if we go back to the 36th International Symposium on Combustion, so in 2016, this was in Korea, there were 4 papers that were on ammonia. We go to then the following Dublin Symposium, there are 7 papers. We then go to the Adelaide, Australia conference, which happened virtually, but there were 23 papers there. And then in Vancouver, 41 papers. And if we were in a classroom right now, I would ask for a show of hands to see how many papers people think were actually published most recently in our Milan Symposium. Fortunately, we're on Zoom, so I'll just give the answer. But essentially, there were 91 papers presented at the Milan Symposium on ammonia. And so this really is a significant area of research for us. And what this means, though, is that there's a lot of data out there, right? There's 91 papers just on this one fuel, or this one fuel mixed with other fuels. And so there's a lot of data, and there are also a lot of kinetic models. And so this is kind of we're at a time that has no precedence, where all of a sudden a lot of us are coalescing around the same problem. And so a logical question to then ask is, are the kinetic models that are being published and that are out there, are they good enough? And how do they stack up against the vast amount of experimental data that is out there? And so in order to try to understand this question, I actually looked to many members of our community here. And so what I'm showing here, these are just 7 select papers that I chose that basically are looking into this question of, if we have a lot of kinetic models and we look at many of them and we compare their performance to large data sets that are available to us, how do these models stack up? And so I chose these specifically because that was basically the point of a lot of these review papers, and they're looking at many kinetic models. I've shown, for example, the number of models here that are investigated. So they ranges from 5 kinetic models up to looking at 36 different kinetic models, and then comparing those with experimental results. And so just to give you some highlights, here are some snippets of what these papers found. So in this Kaka paper from 2020, also should note that all these papers are from 2020 or more recent. So as we go down the page, this is going forward in time, so starting in 2020. But so this first paper, upper left-hand corner, by Kaka et al., mentions that none of the mechanisms were able to reproduce well the profiles of NO, N2O, and ammonia concentrations in flow reactors. Shav and Liz paper says a common issue is a lack of reaction rate measurements at high, mid-range, and low temperatures, inhibiting accurate modeling across the entire temperature range. The Valera Medina paper says none of the models are capable of accurate predictions over the range of conditions investigated. It goes on. I won't go through all of them, but basically the gist here from all these review papers is well summed up, I'd say, by this sentence from the Gerha paper of the group at Aachen. But basically, none of the models delivered satisfactory agreement across all conditions, emphasizing the need for further improvements. So this paper is from 2024, this year. And so as an experimentalist, I then, ask myself, okay, well, how do we further improve these kinetic models, right? And what are the experimental targets that are needed? And so a way to first understand this problem is to look at what is the experimental data that's out there that is already available to us, and how can we either supplement or add to that experimental body of work to provide more value. And so if we focus just on this Gerha paper here, I looked into essentially what was the data that they were using, and so where do these experimental targets come from? And so if we break it down by facility type, they were looking at just over 5,200 data points for their analysis. And so we look at where those data points came from, but half of them are from flow reactors, a quarter of them are from jet stirred reactors. So these are species measurements typically. And then we have laminar flame sea measurements contribute. So those are measurements that were conducted in constant volume vessels or heat flux burner. And then 8% of those data points came from shock tube experiments. So now I am a shock tube person, so that means that I'm interested in that 8%. I want to know, what can I add to this data set that would help further improve these kinetic models? And so if we dive into that 8% of experiments, where do those actually come from? Or what types of data are we getting from the shock tube? And so the vast majority of those data points are ignition delay time measurements. And so that's a global property, right? So it's not necessarily telling us very valuable information about the reaction pathways or the performance of the kinetic model, other than in a global sense. But then the remaining data points are speciation measurements, so species measurements in both pyrolysis experiments and oxidation experiments. But what we'll note is that there are very few pyrolysis data points that are available for use at the moment. So diving in even further, as someone who does shock tube research, I do specifically laser absorption spectroscopy, pair that with shock tubes. So what I wanted to understand is then what of those oxidation and pyrolysis data sets over here for measuring species, what are the species that are actually being measured? And so here's a table, a lot of words on the screen at the moment. This table I adapted from originally from Sean Cleese, who at the time was a PhD student in the Hansen group. And so this is from his dissertation, although I added to it to include some more recent works. But essentially, this is looking at all of the shock tube experiments that were conducted using laser absorption spectroscopy that I was able to find, that we were able to find. And one interesting note, first and foremost, you see that in the past 2 years, there have been more studies published on shock tube work looking at ammonia with laser absorption spectroscopy. More studies published in the past 2 years than in the previous 38 years combined, right? So it's just an interesting historical tidbit there. But so yeah, what are we measuring in shock tubes using laser absorption spectroscopy in order to get time resolved measurements? And so what we see here, the most commonly measured species is ammonia. That makes sense. And I'll kind of go down based on decreasing data availability here. And so the next commonly measured species is then NO, nitric oxide. After that, we then have water also being commonly measured. And then we start to get into the sort of data scarcity range where we have fewer experimental studies on certain species. So for example, OH and NH2, both of these species have only been measured or published in 2 different studies. And then finally, N2O and NH, we see that there's really only been 1 study each focusing on those 2 species. So as an experimentalist, I would look at this list and see, okay, well, perhaps we need more data in more areas, and perhaps this can help guide some of the high value items that we need to measure. And so coming out of this type of high level analysis, we conducted a shock tube study. And so the goal of this study was to study ammonia oxidation in a shock tube using multiple simultaneous time resolved optical diagnostics. And so the overarching goal here is really to generate a comprehensive multi-species data set that could be compared with kinetic models. And so just to summarize our experimental conditions, so we were looking at ammonia with oxygen dilute in argon. So our dilution ratio was, our rate was about 98%. And we were limiting our experiments at this point just to stoichiometric conditions. So that ends up basically meaning that we have 1% ammonia in the shock tube, 0.75% O2 in the shock tube. The temperature range we looked at was 1700 to 2500 Kelvin, 2 atmospheres. And for these experiments, we also seeded in 0.5% of CO2 in order to facilitate temperature measurements. And so in the end, we were able to conduct 7 measurements simultaneously in this suite of experiments. And so first one, we used a diagnostic to measure room temperature ammonia. So this is specifically to measure fuel loading in our experimental setup. And then we had a number of time resolved diagnostic measurements. And so measuring temperature, ammonia, again, so now this is at high temperature as it's reacting, nitric oxide, NO. And then we also had qualitative emission-based diagnostics to look at excited OH radicals and NH2 radicals. And then finally, we were also using our OH star traces in order to calculate an ignition delay time for all of these experiments. So here's a look at what this actually looks like in the lab, right? We're measuring a lot of things, so it ends up looking very busy. But so just some overview. We're conducting this research in a shock tube that has just over a 14 centimeter in diameter. And we're taking these measurements 1 centimeter from the end wall. And so this is looking at a cross section of the shock tube. And then we have basically 3 lines of sight going through the shock tube that we utilize and pair with these different diagnostics. And so I'm just going to step through them one by one, or 2 by 2 in some cases, in order to sort of break this down into a more manageable bite-size story here. But so first and foremost, here on the left, this pink diagnostic, this is what we use for measuring fuel loading. So this is room temperature ammonia. And then second diagnostic, we use 2 lasers to target 2 different wavelengths to measure temperature. So I'll take a second to talk about both of those diagnostics first. And so for measuring our room temperature ammonia, we implemented this in order to basically reduce our uncertainty in our knowledge of the amount of ammonia we have at the beginning of each experiment. And so for those of us who have been doing some ammonia work, we know that it's very sticky, right? And particularly when you have a very large, cold stainless steel experimental facility like a shock tube, the ammonia likes to adsorb and stick to the walls. And so a common approach for dealing with this is to passivate the system. So that means you would basically flow some ammonia or a mixture into your facility. And in our case, we're flowing 5% ammonia and argon into the shock tube. We let it sit for 3 minutes, and then we vacuum it out partially, so down to about 100 millitorr, and then we fill with our final mixture that we're interested in studying. So the idea here is that you're looking to fill up those adsorption sites on the walls of the facility. But we want to confirm, right, that that's actually working, that we're actually getting the right amount of ammonia into the facility at the beginning of an experiment. So we use this diagnostic. So here we are targeting the nu2 band of ammonia at roughly 965.5 inverse wave numbers, inverse centimeters. And we're using a scan direct absorption measurement approach. And so this diagnostic was originally developed and published by Rito Sur from the Hansen group a few years ago. But here's a look at a typical scan over this absorption transition that we're targeting. So we essentially fit this with a void profile, integrate, and then we're able to then back out the mole fraction of ammonia. On the far right here, this is a figure from Rito's paper here, but you're basically showing, if we're focusing on this specific region in the infrared, here's what we see in terms of other competing species. So oftentimes we have to deal with water or CO2 when taking these measurements. So how does our passivation approach work? This is an interesting just sort of side note over here, which is if we now try to put 1% ammonia in the shock tube, for example, and passivate, and we use this diagnostic to then characterize how much ammonia ends up in the shock tube. What we'll notice is that even with this passivation, we see something on the order of 8 to 10% fuel loss. And so again, it's worth noting this is for a very dilute experiment, right? Where even losing a little bit of the ammonia really has a big impact on the overall amount of ammonia that makes it into the gas phase. And so I think one of the key takeaways here is that really only through direct measurement of your fuel loading can that adsorption loss be accounted for or compensated for, right? If now we know that we are losing about 10%, even with that passivation approach, we would then add a little bit more to ensure that we are getting 1% in the gas phase at the start of each experiment. And so I think that really can't be emphasized enough. And there have been a few other papers that have come out also emphasizing this point. There's a paper from Mathieu, Gregoire, and Peterson at the symposium, also basically pointing this out, the importance of that. If you're running dilute experiments for kinetics, it really is important to measure your initial ammonia fuel loading. The second diagnostic I mentioned initially was this temperature diagnostic. So here we are using CO2 to measure temperature. So we're seeding 0.5% CO2 into each experiment. We're targeting 2 absorption transitions. So this is the R66 and the R100 transition, basically right around 4.2 microns. So over here you can see the cross sections for those 2 lines, as well as on the ratio of those cross sections. And so we can use the ratio of absorbances at those 2 wavelengths and knowledge of the line strength as well as the lower state energies to then back out a temperature. So back to this complicated diagram, the next set of diagnostics that we were using, this is a combined diagnostic that allows us to measure both ammonia at high temperatures. So this is as it's reacting in the experiment, and then also NO. And so I'll just point out that this utilizes a suite of lasers, or a laser system in the ultraviolet. So this is sort of a cutting edge laser system that is new in its application here to study ammonia. So I'll talk a little bit more about that. So historically, right, I showed that table earlier where I showed that their NO has actually been measured quite a few times in shock tube experiments. But one of the interesting things to note is that it's always been measured in this 5-micron region, roughly. And I'll show some plots on the next slide, but this is a busy region, and there's also not a lot of absorption. NO doesn't absorb very strongly in this region. So what that means is that there's a number of tricks that often need to be played in order to get high enough signal to actually use diagnostics, NO diagnostics based on the infrared. And so, for example, in this case, in some of these studies, N2O is being used as an oxidizer, but then you end up with some interference from N2O. What's often the case is that people will start adding, or have to add more ammonia, so have a higher initial fuel loading, so on the order of about 5% in order to have high enough NO levels. Or NO is being added to the test gas, either directly or through a precursor in order to, again, boost those NO levels. Or some more complicated optical techniques like wavelength modulation spectroscopy are being used in order to really be able to pick out those signals from the noise. And so again, those previous measurements were all typically taken in the infrared. And so our current diagnostic that was developed and really rehoned for this work probes now NO in the ultraviolet, so at around 224.8 nanometers. And so this diagnostic was actually originally developed by a student in the Hansen group, initially for atmospheric research studies, so looking at oxygen, nitrogen, and excited states. And but here we are now just applying it to study of ammonia and NO formed in ammonia oxidation. So to really hammer home the advantages of moving to the ultraviolet as opposed to the infrared for this diagnostic, I'm showing here in the top, these are NO line strengths in the infrared. So this is simulated using SpectraPlot, a great tool. And so these are the line strengths in the infrared. On the bottom, we have the UV line strengths. And just one thing to note, the numbers are a little hard to see, so I just showed the numbers that are at the top of the axis, the y-axis here. But basically, we get a 3 order of magnitude increase in the line strength just moving from the infrared to the ultraviolet. So this means that we are much more sensitive to NO, just moving wavelength range, essentially. Also, by moving to the ultraviolet, we're able to avoid some of the problematic water interference that previously was kind of washing out the NO. So if we look at this plot in the bottom left here, this is looking at absorbance of NO in the infrared and comparing it to water with comparable amounts. And so basically, the black lines are the water and the red lines are the NO. So what that means is that in the infrared, we're often competing to try and pull out these very small features in order to, and we're really dancing around the water in order to try and pull out useful data. However, one of the issues that we do have in the ultraviolet is that now we have ammonia in the system, right? And so ammonia also absorbs in this UV range around the 224 nanometer range. And so one of the good things, though, is because ammonia is a larger molecule, it has a very broad band absorption spectrum in that region. And so on the left here, this is looking at cross sections of NO in the black and ammonia in the blue here at this 224 nanometer range. And what we see is that if we are measuring NO at the peak where we want to measure it, we find that it is competing with water. However, if we then use an online-offline approach, this means that we would run 2 experiments. So one, park the laser at the online wavelength, then rerun the experiment at the offline wavelength. The offline wavelength basically gives us the absorbance due to ammonia. And because that is constant between the 2 wavelengths, we are then able to subtract it from the measurement of the online wavelength. And so again, because we've now shifted to the UV, this approach allows us to detect NO down to concentrations on the order of 100 ppm, which is very valuable. And we're able to do it with a measurement uncertainty of about roughly 10%. So yeah, I think the main takeaway here is that by using this new UV diagnostic, we're able to get high SNR measurements of low concentrations of ammonia and NO. So back to our schematic here, and I want to highlight the last 2 diagnostics. And so these are qualitative diagnostics. We're looking at emission, not absorption, emission from excited OH radicals. So here we're just looking at light as it comes out of the shock tube, and we're using a bandpass filter in order to capture light at 313 nanometers for OH star detection. And then on the other side of the facility, we are similarly collecting emission. This is now centered at 600 nanometers in order to capture excited NH2. As I mentioned, we're targeting these two wavelengths for these emission measurements, and we're using the OH star trace, so it's here in blue. This is a typical experiment. We've got the pressure trace in black, so incident shock, reflected shock, and then relatively constant pressure over the experiment. We have our NH2 trace here in red, and then our OH star trace here, NH2 star, and our OH star trace here in blue. And so typically we will find that point of maximum slope, extrapolate it back to this baseline, and that's what we would then take as our ignition delay time. And so our uncertainty and ignition delay time is roughly plus or minus 10% for these experiments. All right, so now I'd like to talk about the results from this experiment, these set of experiments. So I'll first talk through the ignition delay time measurements, then I'll get into the time resolved measurements. So I'll start with the temperature and then focus on the NO and NH3 mole fraction measurements. I'll then take a kind of pause to do some kinetic analysis and kind of introspection on what we learned from these NO and NH3 mole fraction measurements. And then I'll end by talking about the emission traces from NH2, excited NH2. So ignition delay time. As I kind of emphasized a little bit earlier, we often are concerned about adsorption and having the right amount of ammonia in the experiment. And so by having that fuel loading diagnostic that helps us accurately quantify the amount of ammonia in the system, but a common sense check is often to just make sure that we get the same answer as other people in the community, right? In order to ensure that we're all doing these experiments correctly and that we're getting consistent results. And so it's typically our first stop, especially if it's a new fuel or a fuel that can be problematic. And so here, this is now comparing to work done at Texas A&M. So this paper by Mathieu and Peterson. And so their points are in the black, our points are in the red. And essentially, this lends us confidence that basically what we're seeing in our shock tube is consistent with what others are seeing. So with that sort of sanity check out of the way, here's a look at some of our data points for the experiments that were paired with the species time history measurements. And as I mentioned, there's a lot of kinetic models out there for ammonia, right? And so it's always a question of which one do you compare to? And after some literature survey, we had found that this model by Peter Glarborg and colleagues, so from 2018, it was found that this one, as well as this Al-Tarifi ammonia pyrolysis submechanism, that they both have been relatively good at replicating the species time histories in a lot of these ammonia oxidation experiments. And so we decided to compare with these models, although one could compare with any number of kinetic models here. And so solid red line is using the Glarborg model as published, and then the dashed line is where we've now replaced or added the submechanism from the Al-Tarifi model into the Glarborg mechanism. And this is again inspired by previous work by others in the literature where they found that was able to, that addition of that submechanism was helpful in more accurately or more satisfactorily replicating the species time history measurements. So we see that just alone, the Glarborg model overpredicts the IDT by about 30%. So this means that it's predicting that these IDTs are slower than they truly are. But when we add in that pyrolysis submechanism, we find that the model captured those measured IDTs within about 10%, which is within our uncertainty of those measurements. So good to see that we actually are able to replicate those ignition delay time measurements. This is kind of a key point, though, is that we're able to replicate with these models, replicate the global property of ignition delay time. And so then we want to understand, okay, how do these models now do if we look a little more detailed and start looking at species time histories, for example, or temperature time history. So next, as I mentioned, we used a CO2-based diagnostic to measure temperature. And so the main takeaway here is that the magnitude of temperature rise over this ignition event is well captured by both the Glarborg model as well as the Glarborg model with the Al-Tarifi submechanism. And that's not a surprise necessarily. If you look at the thermophiles, thermodynamic properties are nearly identical in both of the models. But we do see a slight difference just between the two model predictions. But this is likely due, again, to those differences in the ammonia pyrolysis reaction rates. But overall, we would say that the models capture this temperature trend quite well. And it's really just a very minor increase in temperature, right? So on the order of about 1 to 2%. Next, let's look at our ammonia and NO species time history measurements. And so I've broken this down. We had a lot of data. This paper is now published actually in Combustion and Flames. If you want to look in a little more detail into the results that I'm showing here today, I encourage you to go to check out this paper. There's a lot of data, but so to make it a little more manageable, what I'm showing are just one or some low temperature results and then some high temperature results to kind of bookend what we are seeing in the experiments. So here's looking at low temperature. And so this is the black line is the measured ammonia trace here. So we again see that it decays here, and then we then form NO. And the red lines again are these model simulated results. So what we see is that both models, they initially underpredict the rate of consumption of ammonia, and then ultimately overpredict that rate of consumption as time goes on. This is again at the low temperatures. This is at roughly 1780 Kelvin. And if we look at this is a similar but a different low temperature conditions, so this is about 2000 Kelvin. Here's the NO formation. And so interestingly enough, we see that the Globberg model seems to capture pretty well this initial rate and timing of NO production. When we add that ultrafiltration submechanism, we've now skewed this sort of pre-oxidation chemistry, and we really skewed the composition of NO, or the mole fraction of NO that is being simulated. And then we see that both models overpredict this NO plateau value. If we now look at the higher temperatures, we see it's sort of similar trends. And so again, black is the ammonia measurement. Again, we see there's some disagreement regarding this late time consumption of ammonia. And then once again, we do see that at early times, the Globberg model, as well as the ultrafiltration model, or with the ultrafiltration submake mechanism, they are capturing that initial increase in NO, but then they are over-predicting the rate of NO production, and then they are both also over-predicting the NO plateau value. So as another metric for comparison, we then wanted to look at these NO plateau values more broadly. And so here's a look at what those plateau NO mole fractions are as a function of temperature compared to both models again. And so the main takeaway here is that we do see significant discrepancies between these experimental NO plateau values and what the models are simulating. And so, for example, near about 1850 Kelvin, this Globberg model overpredicts the NO plateau value by about 60%. But if we then add that NH3 pyrolysis submechanism, that is then cut in roughly in half. And so we are able to get closer to the experimental value. But again, this is looking at plateau values. And as we saw in the time resolved measurements, right, even if we do add that submechanism, we are now off in our production rate and then of NO. And so it's kind of 6 of one, half a dozen of the other, right? We're able to improve the plateau on the plateau values, but we're not capturing the time resolved chemistry, which I think is an important point in and of itself that really argues for the validity and the importance of time resolved data, right, in order to help guide optimization of these models. So overall, we see that these models overpredict the amount of NO, the plateau value. But I just wanted to make a note here that we found in the literature that other recent studies actually have conflicting observations if you were to look at something like this, these NO plateau values. So this paper by Zhu et al., where they're looking at ammonia and oxygen and argon, they found that the Globberg model actually captures the peak NO mole fractions quite well and the formation timescales. However, conversely, in the Zhang et al. Paper, they found, this is where they were looking at ammonia mixed with some other hydrocarbons, so methane and ethylene, for example. They found that the Globberg model shows reasonable NO formation timescale agreement, but it underpredicts the NO plateau values near PM1. And so this is very symptomatic of where we're at right now, which is that you compare the model results with various different types of experimental results, and we find different answers. And so one of the key things then as an experimentalist I want to understand then is what is leading to these discrepancies and the inconsistencies here. And so to dive into that, we'll typically do a sensitivity analysis. So I'm showing sensitivity analysis results for ammonia and NO. So ammonia is on the left here. And so this is looking at sensitivity of ammonia mole fraction to various reactions. And then on the right, this is sensitivity of NO to various reactions. And sort of if we just look at the colors here, so basically we see some of the highest values are first this dash dot blue line. And so this corresponds to this H plus O2 goes to O plus OH reaction. It's not a surprise. Next, we have this dashed pink line here, which is this pyrolysis initiation step. So this is NH3 plus M goes to NH2 plus H plus M. And then third, we have this green dashed line, which is this H atom abstraction by H atom reaction of NH3 plus H goes to NH2 plus H2. So that's just looking at the ammonia sensitivity. If we now come over to the NO sensitivity, we actually see the same culprits here, right? So dashed blue or dash dot blue, this is the H plus O2 reaction. Dashed pink, this is again that NH3 plus M reaction. And then in the dashed green, this is now that again that NH3 plus H reaction. So looking at the sensitivity analyses, particularly at these early times, we see that basically it's dominated really by these three reactions. So reaction 1, H plus O2 goes to O plus OH, or reaction 2, NH3 plus M goes to NH2 plus H plus M. And then reaction 3, NH2 plus H2 goes to NH3 plus H, or really kind of the backwards of that. So then the question is, okay, well, what is our state of knowledge of these reaction rates? Are these actually the problem? Are these leading to us having these disagreements between the experimental results and then the model results? And so if we go one by one, here's first looking at that reaction 1. This is actually one of the most well-studied reaction rates that we've considered in combustion chemistry, simply due to its importance in all things oxidation related. And so what I'm showing on the left here, this is a plot that we included in a paper earlier this year, but the data points here are experimental measurements of this rate coefficient. And then the lines are what different kinetic models are using for those rate coefficients. And so these are just some common models that we're used to seeing and using for small molecule chemistry. And so what we do find, though, is that most of the kinetic models at this point have really converged on a common or at least a similar rate constant for this reaction rate. And so this one is likely not a culprit in terms of leading to our disagreement that we're seeing in the ammonia measurements, because it has been so well studied and models have mostly converged on a common rate coefficient. How about reaction 2? So now this is looking at the NH3 plus M reaction, goes to NH2 plus H plus M. And so actually for these plots, I had mentioned this work earlier, but there's this review paper by Alison and Liz in Chemical Reviews. It was published in 2020. And they actually do an excellent job of really in detail going through all of these relevant reaction rates and assessing the experiments and the theoretical calculations that have been done for these various rates related to ammonia oxidation and pyrolysis. And I've made some of these great plots that I'm showing here. So this on the left here, A and B, this is figure 19 from this paper. And so this is the rate coefficient at 1 atmosphere. And so on the left here, this is just looking over a broader temperature range. And on the right here, this is zooming in a bit. And so what's interesting to note, well, I'll add first on the far right here, the high pressure limit for this reaction rate is at about 0.3 megapascals or 383 atmospheres. And so here also results for this rate coefficient at the high pressure limit. But what we see across the board here is there is relatively strong consensus, at least among these rate coefficient measurements at high temperatures. And so it's showing that we are really kind of getting consensus on what this rate coefficient should be, experimentally at least. One of the points that is made in the paper, this review paper, is that the high temperature rate coefficients actually overestimate the reaction rate at lower temperatures. And so that is a fair point, but I would also argue that at least for our combustion application specifically, this really is the temperature range of interest for us. And just for reference, the temperature range that we're looking at in the shock tube experiments that I've been talking about spans from about this 0.4 up to about 0.55 inverse 1,000 over temperature range. So, okay, this reaction rate is also probably maybe not the culprit here. So now let's look at reaction 3. This is this H abstraction reaction. And there actually have been 5 experimental studies to look at this reaction rate. They all span or were conducted between 1965 and 1990. And what we see is that, again, they do kind of collapse on each other, but we do see larger discrepancies between theories. So these solid lines here are theoretical calculations. And we do start to see larger discrepancies at both the high temperature range as well as the low temperature range. But otherwise, I would overall say that there's pretty satisfactory agreement between experimental results and then these theoretical calculations. So what does that mean? I've looked at these top 3 reaction rates, and there's not anything immediately jumping out in terms of a further need for experimentation per se. So then I would go back to the sensitivity analysis, and if we say that perhaps we need to look elsewhere for high uncertainty reaction rate targets, it helps to then look at what are some of these other reactions that are competing for the species that we see in some of these important reactions. So things like NH2 or H or NH, right? What are some of these other reaction rates that we see as important here? And so one of these is this NH3 plus NH goes to 2 NH2 reaction. And one of the interesting things is that there actually is no experimental work, or there's very limited work that I could find on this reaction rate itself, right? And so perhaps that's where we are now as a community, that we've kind of hit a lot of these bigger reaction rates, and as experimentalists have measured a lot of these more significant reaction rates, but perhaps now it's time to start honing in on some of these more minor reactions that are competing for these radicals that are really important in these early stages. And so that would also indicate that it's important for us to measure things like NH2 and NH, not just the ammonia and the water, and then, for example. All right, and so then the final set of results that I want to talk about, these are the emission results. So this is excited NH2. And so unfortunately, there's been some work looking at excited NH2 submechanisms, but the vast majority of the kinetic models out there do not include submechanisms for excited NH2 radicals. So it's actually hard at the moment to make reliable comparisons between NH2 star and model predictions. So what I'm showing here, the black line, this is the emission trace, the NH2 star emission trace that's measured, and then the red lines again, solid is the Glauberg model, and then the dash is the Glauberg with the Altrafy ammonia pyrolysis submechanism. And so I'm comparing apples and oranges in a way, and that the black line is excited NH2, and then the red lines are NH2, so ground state NH2 as predicted by the models. But this still can provide us with some interesting areas for comparison and observations. And so what we first see is that the rate of production of NH2 or NH2 star is not accurately captured by these model trends per se. So we see at the beginning, we do see agreement, at least with that Glauberg model, if we're assuming that NH2 is a surrogate for what we expect to see with NH2 star. But then we do see typically that the experimental trace is a little bit steeper at first, and then the models are too steep compared to the experimental measurements. Another thing to note is where this peak, where we expect this concentration to peak. And so depending on which model or version of the model we're looking at, we see that we're not actually capturing this peak in NH2 star. So at the low temperatures, that's the case. And we also see the same case at the high temperatures here. We often see that this peak is falling between these two simulation results. And so I won't be presenting any sort of sensitivity analysis. I think this is really a key area for future work, right? So being able to really compare directly model simulation results for some of these radicals like NH2 to experimental measurements. So that would require basically measuring NH2, ground state NH2, or further developing kinetic models for excited NH2. And so I think that is an area of future work, and certainly an active area where we're in the experimental world, we are pushing towards that, right? So being able to also measure NH2 directly, so we can do that direct comparison. So stay tuned for future work. So that brings me to the end here today. So I just wanted to summarize and point out some key takeaways. I think as an experimentalist, right, and in this area of ammonia where there's a lot of work, a lot of experimental studies that are coming out, it's important for us to identify high value experimental targets, right? So maybe we don't necessarily need more ignition delay time measurements or global properties, measurements of global properties like laminar burning velocity. Yes, it's helpful, but in order to actually really hone in and answer some of these questions these remaining questions that we still have about these chemical reaction pathways, it's going to require very specific and targeted measurement campaigns on things like time resolved species measurements and that sort of thing. And so from the analysis that I presented today, some of those key species are those radicals and those intermediate species that are being formed both in ammonia pyrolysis as well as oxidation. So things like NH2 or NH. Also the ability to measure quantitatively excited states, so NH2 star, for example. And then just really wanted to circle back to this particular observation, which is that I encourage all experimentalists to have a way to directly measure your ammonia fuel loading in your experiment, particularly if you are running dilute experiments. And it's kind of a challenge, right? Because a lot of these kinetics experiments, we want to run them dilute so we can simplify them and simplify the data analysis. But then we have this struggle then that you will impact your fuel loading if you are running dilute. But I think that really just is highlighting the importance of having a diagnostic that allows you to be sure of how much ammonia you actually have in your system, so that we can then trust the experimental results that are coming out of the setup. In terms of high value experimental targets for reaction rates, I highlighted really we're at this point of looking at sort of secondary pyrolysis reactions involving radicals and intermediate species. And so one particular reaction that came up in the analysis was looking at this 2NH2, this NH3 plus NH reaction as one key point. But I would encourage everyone who is doing various bits of work in ammonia, whether that's ammonia plus X or pure ammonia, to do this type of analysis so that you can understand what are those high value targets, and what can we get out of our measurements that's adding to the literature in ways that we haven't seen previously. So to get back to this initial question, ammonia kinetics, are we there yet? I would say not quite yet, but we are getting closer. We are asymptoting, and I think there is still, though, a lot of valuable work to be done that will help us get over and get to the end of this, or get to a point where we can say that these kinetic models are converging and that they are satisfactory. And so finally, I'd just like to acknowledge some people here. So first, I'd like to acknowledge the Hansen Research Group at Stanford University. So the PI, Professor Ron Hansen, as well as the team of students or postdocs who contributed to the experimental work here. So Dr. Sean Cleese, Taylor Ralt, Dr. Miguel Figueroa Labastida, and then also Spencer Barnes, great team of students who ran the experiments and put in the long hours to get these diagnostics to work. And also I would like to acknowledge the financial support from Total Energies, as well as various student funding mechanisms, so NSERC Canada, Stanford University, AFOSR, and then finally the National Science Foundation. So with that, I'll wrap up, and I'd be happy to take any questions. Thanks for tuning in today.
Okay, thank you. Thank you very much for this very interesting talk. And yeah, now the floor is open for questions. So everyone, if everyone from the audience wants to ask a question, please feel free to ask, raise your hands or unmute yourself.
Yeah, so I see one question in the chat. This is from Hao Tong.
Oh,
and so it says,
okay.
Hi, Alison. Could the data from the counterflow burner also be a useful experimental target for ammonia kinetics? That's a great question. So one of the reasons that we typically rely on shock tube experiments is that we are able to separate out any of the complications that would be added by having to take into account flow or spatial distribution or transport properties, essentially. We're able to just hone in on the 0D chemistry and time. And so that's one of the reasons that we like to take a look at those experimental targets specifically. But in the counterflow burner, I mean, it's useful in other ways, right? So we're looking at things like lean blow off or pushing the bounds of where ammonia is usable, essentially. And I do think, though, if you were looking at things like additives, or if we're adding something to the ammonia and trying to understand, say you're able to take a 2D map of some sort of species or something like that, then you can try to look at trends as you're changing those in order to understand what could be causing the concentrations that you see. And so, yes, I myself am not a counterflow burner person, but I think one of the keys here is the more detailed information we have. So instead of just looking at strain rates, for example, but looking at something like a species concentration, I think that type of data will give us more information, more useful information than some of those global properties that are dependent on a combination of kinetics as well as transport and other phenomena in the experimental setup. So that's my 2 cents. Thanks.
Any other question? If not, I would like to ask a question. You showed experiments at 2 atmospheres, so I'm wondering what's the scenario if we go towards a higher pressure. What's missing there? If you can give us a quick overview.
Sure, yeah. So I haven't actually done the analysis there per se. If we go back though and take a look at what is there. And so you will see and notice that at least in the shock tube realm, a lot of these experiments are limited to lower pressures. And so I haven't done the sensitivity analysis, for example, to see does the chemistry, do the important reactions change. But I think also from the general review papers that I showed on the sort of previous slide here, where they are looking at all of these data sets at various pressures as well as equivalence ratios and different compositions and that sort of thing, we really aren't seeing consensus, right? And so I think that does point to your point. It is important that we aren't just taking measurements at one equivalence ratio or one pressure, right? We do need to kind of branch out and push to higher pressures as well. And so I don't have an answer for you specifically in terms of what the implications are for important reaction rates per se, but we need more data in those areas, right? So I think, again, the just generally the approach of looking at what is out there and therefore what is not out there is kind of an important one in order to help guide the future work.
And I have one other question. If no one from the audience has any, that I would like to ask you is when you see agreement, when you look at the agreement between the experiments and the kinetic models, how important is for you to also check that actually to account for the uncertainty of the kinetic models? Because I'm guessing that there is a certain uncertainty not only in the experience but also in the kinetic or the kinetic parameters of the models. Have you or are you planning to do any work actually taking into account the uncertainty that is attached to the kinetic model itself, or you just care about the nominal values and you see it won't work and you just assess that, and these if the fact that maybe the model uncertainty
encompasses the experimental So that's a great question, and this is something I love talking about because I think we are often at war with each other, those who do experiments and those who do the modeling, where, I think we often hear from the modelers, oh, we need more uncertainty analysis on the experimental side and vice versa. And so we, at least I personally, try to take great pains to try and accurately quantify the experimental uncertainty so that way it can be accounted for modelers who are looking at the experimental data. And so you can see here, for example, we do quantify our uncertainty in the experimental data. That means that then, and the reason for that is because we are most intimately acquainted with our experiments, right? And therefore are the best ones to assess and understand the different factors that are leading to that uncertainty. And so if you read our paper on this work, there is quite a detailed overview of what the factors are that lead to these uncertainty values that we've calculated. To your point, I'm not actually showing kinetic model uncertainties here. Part of that is that it's often difficult for us as experimentalists to accurately assess that. What we've done in the past, though, is perturb different things. So either the reaction rates, right, that's where we're getting the sensitivity analysis, or perturb things like the thermodynamic properties in order to see how that changes things. So at the moment in this work, for example, we did not quantify the model uncertainty. But one of the key things that if you're looking at something like this slope or the rate of change, right? So that disagreement isn't necessarily going to be accounted for in the uncertainty of the model versus the experiment. But I think that is a great point, that also moving forward on both sides, right? We should be very transparent about our uncertainties. So as we're honing in and asymptoting towards understanding ammonia chemistry, right? We're now looking at details, right? Secondary reactions, or really the uncertainty is starting to play a bigger role. So I agree. So we have not done that here, but I think that's a great point, that for those of us on both sides, whether modelers or experimentalists, we should be taking pains to try and account for that and understand to what degree is the disagreement due to uncertainty.
Okay, we have a question from the audience. Actually, two questions from the audience. One is from Yuki Murakami. Thank you for the great lecture. I've seen large discrepancy in NH3 flame speed predictions, especially on the rich side. Do you have any opinion? Do you think it's also coming from NH3 absorption on the wall?
Good question. So We have done a little bit of work looking at ammonia flame speeds. This is specifically using our approach where we're looking at them in a shock tube. Adsorption is always a problem. So I without having actually looked at the data itself and looked at the experimental facilities used for this, we could assume something like we're using a counterflow burner, let's say, for the sake of argument. The question would be what you write, what is leading to that discrepancy. I don't have an opinion at the moment since these are 0D experiments that I've been presenting, but I think it could be coming from adsorption. But if you were looking at a counterflow burner, for example, a lot of that is controlled by MFCs, right? So mass flow controllers, where you're controlling the flow of things into the facility in the burner. It's going to depend on the setup. So I don't have a good answer for you at the moment, but I think even so, the analysis approach here is valuable, right? So what you would want to do is look at the flame speed sensitivity analysis typically. So in the rich side specifically, typically you're going to find a lot of the similar reaction rates, but as you go rich, right? I was showing stoichiometric here. So as you go rich, you will start to see some other probably fuel bound reactions that are ammonia related reactions that are becoming more important. And so hard to say on the adsorption question, but I would say, again, sensitivity and the rate of production analyses are really going to be your best friend here in terms of trying to understand those differences. So sorry, I don't have a good example for you because I have not looked at those studies in detail. I see the Haotong question, the second one. Sure.
And that was a satisfying question for
it looks like
answer
thank
for
you for the next question. Sorry, happy to talk offline later if you'd like. So now about the NO plateau values. So the model overpredicts the NO plateau value, but other studies show conflicting results. Yeah, and so that's sort of what I pointed out here is how do we determine which data is reliable among a lot of papers? And so this is a great question. If we go back to, let's see, if we go to the NO plateau, I already passed it, the NO plateau values here. So again, right, what we're seeing is that these models are over predicting the amount of NO. But then I pointed out that there's some of these other studies. And so if we look at these other studies, this is the Zhu et al. Study, and then also the Zhang et al. Study. So if we go back actually to the table that I have of all these studies, here we go. So the Zhu et al. Study is, I believe this one. So this is where they're measuring NO. They measured NO in 2 cases, but if we look at the different conditions here, so they are, I believe, let's go to the other NO one. This will be faster if I simply get out and look here. This is the slide I'm looking for. So in these cases, these experiments are fundamentally different, right? And so the question of which one is more reliable, it's always a tricky question, but they are inherently different, right? So they, for example, are using a higher fuel loading. And so it's 4 to 6% to 7% ammonia, and in that case, and then in the Zhang et al. Case, they are using, in some cases, just different approaches for the measurements. Or they are using things like adding additional species and adding additional concentration of NO to the mixture. And so I don't think it's necessarily accurate to say, well, these are the same measurements, but they're giving different results compared to the models. These are inherently different experiments where certain things are different about them, right? Either you have 5 or 6 times the amount of ammonia fuel loading in that experiment, or you have other species that are present in order to enhance the level of NO for diagnostics to work. And so it's a little more nuanced comparison there where, again, sorry to keep going back to this, but I think doing a sensitivity analysis for that specific experiment where now you have that 6% ammonia and sort of thing, and then comparing it, this is what I would do if I wanted to get to the bottom of this question. I would then compare that sensitivity analysis to the sensitivity analysis I do for my own experiments with the 1% ammonia, for example, look for differences there and see, am I getting the same results? In which case, then I will have to start thinking about, is one experimental technique more reliable than the other? But if I'm getting different results because now I have, different composition in that mixture, then that is a key there for explaining those discrepancies in what we're seeing. And so either way, the model should be capturing these trends, right? Whether or not we have the 5 or 6% ammonia or whether we have the 1% ammonia. But that's basically what would be needed in order to get to the bottom of that question. And then if we find that it's the same reactions that should be dominating both systems, not likely, but if we find something like that, then it's a question of, okay, well, looking into the experimental details of passivation, are we sure about the initial amount of ammonia that's in the system, right? Because that would just initially skew the amount of NO that you're getting, and that sort of thing. And so looking at it as which one is more reliable, we're not yet at that point, I would say. It really is a question of, I think, honing in on the specific experiment and then doing the comparison there subsequently in order to understand what the source of that discrepancy is.
We have another question in the chat.
Hi, Alessandra. Good to see you. I see that there is an increasing interest also in N2O chemistry as a key pollutant. Do you think that further shock tube data can aid in this direction? It seems that from the literature review, there are much less experiments on it. Yes, correct. And so from that literature review, right, we were looking at that earlier. We see that N2O is really only measured in one study previously. And so that one is a little more challenging to measure experimentally simply due to the diagnostics and interfering species that we see, but it is a really key species, right? Because it's actually a intermediate that is formed and then goes away rather rapidly. And then whereas NO, we see it form and then it will stick around for a bit. And so this is, I think, a key species where that will play a big role as we try to understand that formation process of NO, because it typically will go through this N2O. And so, yeah, I think that's a key target as well. So in addition to these radical species, N2O should definitely also be added to the list. And so we should push for more measurements of that as well. Great point, thanks. I'll add it to the list.
Okay, I mean, it was a very cool, very interesting Q&A session. I think we can close it on this question, and I would like to thank you again, Alison, for this great talk, for this great Q&A session. And I see also Alessandro, if he wants to say a word.
No, just thank you very much.
And
thank you. Good to see you.
Okay, thank you everyone also for attending this session, and hopefully I hope to see you soon, this many as you were today. We had our next appointment, and let's thank again the speaker for her time and for her lecture. Thanks a lot, Alison.
Thank you everyone for tuning in. Appreciate it.